everyone, I would like to talk today about the Brouwer's fixed point theorem. So in its general version, it says that for every mapping from a compact convex set to itself, there is always a fixed point. But I will not talk about this general version. I would rather focus on the version in the plane, on a disk. So as an illustration for the theorem, consider a cup of coffee. So no matter how you steer the coffee, there is always one point that will end up right before where it was before we started steering the cup of coffee. So this serves as a good motivation for the theorem. Now let's see some more details. So as I mentioned before, we're going to talk about Brouwer's fixed point theorem. And why do we care about this? Well, in topology, which was its original field, this result is one of the key theorems characterizing the topology of Euclidean spaces, and it has also numerous applications across various fields of mathematics, which include differential equations and differential geometry, and it was used for proving deep results in these areas. And also it appears even in fields such as game theory and economics. And so we proceed to the statement. It says that every continuous function from a closed disk to itself has at least one fixed point. So what does it mean? If we call the continuous function f, then this implies that f of x equals x for some x on the disk, which is what a fixed point is. So the most important things to remember: the function must be continuous, and we also need it to be from the closed disk to itself. And well, we can illustrate this in the real world by, for example, taking a map of the world and placing it on a table. So this theorem says that there will always be a point on the map which is directly on top of the real point within the country. So in my case, this point will be here. So let's see why these hypotheses are important. As I illustrated before, if we take a cup of coffee, for example, and we steer it like this, it will have a fixed point, say this one. But if we take a set with a hole, then we may have a map that goes like this. And, well, it doesn't have a fixed point, so it doesn't work. So we need the set to be convex, and also we need it to be bounded, because, for instance, in this unbounded case, we can have a flow like this, and it will not have a fixed point. So I would like to introduce the outline of one proof. So there are many proofs, and this one I'm going to show here uses the fact that there is no continuous mapping G from the disk, so the closed disk, to its edge, the circle, such that it is the identity in the circle. And we will use this fact, but I'm not gonna prove it because it requires deeper techniques. And so the proof says that by contradiction we assume f of x is different than x for all x in the disk. And so we may define a function which is consider f of x to be this point and consider x to be this point. So we can take the ray from f of x to x, and we define the function h to be the point at which this ray intersects the circle. So notice that two things: h is continuous, and also we can check that h of x equals to x for all x in the circle. So note that if we assume that f of x is different from x, this map is well defined, and we arrive at the contradiction that h of x would be a continuous mapping from the disk to the circle, such that the circle is fixed, and well, this cannot be, so we obtain a contradiction, and we have proven our theorem.